It's just like a layer of feedback. Okay, I can go around and can we just pass the signal? I can go around and talk to you individually, or we can do some group discussions first on some of these questions. It's up to you about what you think would. Or is there any particular one of these that you'd like me to look at? First of all, I think I did question 1 and maybe was it question 3 I also did in the tutorials. Yes?
Can we go through
6?
Yeah.
Okay, good. One last ones. So, as you can see, they split into 2 kinds. There's ones with the summation formulae, and then ones here with the inequalities. So they tend to just be kind of a different flavor. So yeah, how did you get on with question 6 when you were doing it?
Well, I got to a certain point, but I didn't know where to go with it.
Okay.
So
yeah. I'm not surprised to hear that because the inequality ones are kind of harder than equations because when you're in the nub of the argument, trying to do the induction step, when you're developing a chain of equations, it's quite restrictive really because as you develop your expression, you have to keep it the same if you're building a chain of equations. So you're very restricted in the kind of things you can do. Whereas if you're developing a chain of inequalities, there's a lot more freedom because you're making the thing bigger each time or smaller, depending on which direction. So because you have so much freedom or so much, different possible things you might put down, choosing the right one, choosing the correct path can be more challenging than in the equations. Okay. So this result says, question 6, for every n bigger or equal to 1, so these are the positive integers n, that the nth power of 1 plus a half is greater than or equal to 1 plus n over 2. Okay. So it's giving us a lower bound, if you like, on the nth power of 3 halves. Okay. It's still a classic thing for proof by induction, because it's an infinite set of statements indexed by the positive integers, yeah? So we will use induction. So you would have looked at the base case, and I presume the base case is n equals 1, that's the first relevant value. And I think they're both equal to the base case, aren't they? Yeah. So 1 plus a half to the 1 is in fact equal to 1 plus a half. So base case is true. Okay, being equal is part of being is compatible with being greater than being. So having done the induction, having done the base case, you're going to be using proof by induction. So the very next step is to assume the truth of the statement for some general value in the range. So we next assume the result is true for some general k value within the relevant range. Okay? And we're allowed to make that assumption because we've already observed that it is true for k equals 1. So it's not a kind of, we're allowed to assume it's true for some k. So what is the assumption? And it helps to not just say you're assuming it, it helps to actually literally write out what the assumption is, even though it is just replacing this equation, replacing the n with k. But having it on the page in front of you with the appropriate symbols will help in what you have to do afterwards. So we assume that that's true, and now we try and derive the next instance of the result. So now we're going to try and derive the inequality where n is equal to k plus 1. Be confident about it. We won't say try, we will establish the inequality where n equals k plus 1. So this inequality on the left-hand side has 1 plus a half to the power k plus 1. And we want to develop this in a way, but what we want to end up with, put it here in a cloud kind of floating over here to the left, is we want to show that this is greater than or equal to 1 plus k plus 1 over 2. Okay. That's what we require from the manipulations that we're going to do now. And it helps to have that front and center in your vision, so you know what you're going. Okay, so if you know where you're going, it's easier to get. And two things we're going to be using here. We're going to be using just standard algebraic manipulation for powers, fractions, maybe something about basic facts about inequalities behave. But crucially, we will have to use the assumption as well. If your argument is not going anywhere, one of the reasons might be is because you haven't yet invoked the assumption. You haven't yet applied the assumption. So you always try and do that, I'd say, at the earliest opportunity. So how did you proceed from here?
Write it as 1 plus a half to the power of k times 1 plus a half.
Yeah. So factorize this a little bit. So 1 plus a half to the k plus a half. Yeah. And why did you do it? Why did you do it that way, or what's your thinking?
Because like you've got it in the assumption, so you can use that.
Yeah.
But then I didn't know where to go for that.
After that, okay. So you use the assumption at this point. So this means that the assumption says 1 plus k over 2 is no bigger than this. So we can use that here. So this quantity now is greater than or equal to 1 plus k over 2 into 1 plus a half. Yeah? So that's good. That's using the assumption. And we definitely have to do that somewhere along the way. So the fact that we've done it, good. That's an achievement. So, okay, this is where you come to the junction. There's lots of different possible routes, I mean, it's tempting when you see this 1 plus a half, it's tempting to collapse that together as 3 over 2, maybe. You could take this 1 plus k over 2 and write it over the common denominator 2, be 2 plus k over 2. We might choose to multiply these out. There's any number of different ways. It might be you just have to try different things. You might have to come back and rewrite out a clean version of the argument afterwards after you've tried a few false starts and discovered which would work. But the thing to help you make the decision of where to go and what to do and how to manipulate this is to keep your eye on the destination. Okay? We want this thing to be greater than or equal to something. Okay? We've already got the greater than or equal to relation. So we're part of the way towards doing this. We want our thing to be greater than or equal to 1 plus a fraction with k, something to do with k over 2. Well, here it looks quite tempting. We've got our 1s, one here, one here. We've got plus. We've got fractions with something to do with k over 2. So it's not that far away from this. So because of that closeness here, that we want a 1 plus some kind of fraction over 2, because that's kind of sitting there, I'd be tempted to multiply these out to this stage. Okay? So to not do any more inequality work for the moment, but just multiply out these brackets. When you multiply them out, and it is a little bit unnatural to keep this expressed as 1 plus a half rather than 3 over 2. But because of the structure of the thing we're going for, it still might be natural, I think, to keep them separate. So to just multiply out the bracket symbolically, so to speak, and get your four quantities here that come from multiplying an a plus b by a c plus d. Yeah, just multiply that. So we get a 1 plus a half. There's that bracket there. 1 plus a half plus k over 2 plus k over 4. All right. Okay, certainly equal to what we had before. Okay, we've shown our left-hand side is greater than or equal to something. That's what we have to do, shows greater than or equal to something. 1 plus k plus 1 over 2. Here we got 1 plus a half plus k over 2 plus k over 4. It's not a million miles away from that. How close is it? What's the relationship between the thing I'm at now and the thing that I want to get to? Can we emphasize how they relate to each other in a certain way? Can we make what I've got here look more like this? Any suggestions? Yeah.
You can add a half and k plus 2.
Yes, yeah. See that? These two terms here, if we add these together, just using rules of fractions, it'll turn into k plus 1 over 2. And we've already got a 1 there. So that's, having spotted that, I would just go ahead and do that immediately. There's a 1 plus k plus 1 over 2 plus k over 4. And that's good because it shows us exactly how what we have here relates to what we're trying to get. Yeah. So where do we go from there? Very, very, we're extremely close. Prove the base case. We made the assumption. We're trying to establish the next case of the thing, which we know what it looks like. This power is bigger than or equal to this. Here we have this power is bigger than or equal to almost this. So, yeah.
Can you set that as what we've done with the k over 4 as greater than the other side because it's got an extra thing on it, so it's always going to be greater than it? Or not?
So this is greater than
what you've got in the blue.
Yeah. Strictly greater than or greater than or equal to?
Strictly greater than.
Yeah. Now what's your justification for that if I query that?
Because there's an extra term, so it's always going to be greater than.
Yeah. Just maybe a little, well, how do you know that this extra term is, you see, you're forgetting an extra term, but maybe that term could be negative or?
The condition was k is always positive.
Yeah, k is always positive. So k is positive, so this extra bit that we're leaving off is certainly a positive quantity. That's just the extra little kind of, but the idea is correct, yeah. You're just forgetting this part, so this has to be bigger than that. So the justification for that is since k is bigger than 0 from above. It's not any old k, it's some k bigger than or equal to 1. So yeah, that's and this is the importance of having, if you know the destination, literally having it on the page in front of you while you're looking at the kind of, when you're in the middle of the algebraic argument. If you know what you're trying to get it to look like, it just helps you spot the connections and see the correct thing to do. Okay, so that's good. You spot it and you bring those together, you get this. So then you step back a bit and you look at what you've done in total. We've taken this thing here, we've related it to this, and what's the overall summary of all? We got a number of different relations along the way: equals, greater than or equals, and strictly bigger than. But how are those all combined into one single relation that tells me how this left-hand side relates to that right-hand side? Is it equal to it? Is it bigger than or equal to it? Is it strictly bigger than it? When you combine all these relations along the way into one, which is the correct one to use? Which one is the dominant relationship, so to speak?
The last one.
Yeah, the strictly bigger. That trumps all the other relations, really. So we held the left-hand side the same. Then we moved to something which is bigger than or equal to. I'm not sure. Yeah. Then we kept it the same. Then we kept it the same. But then we made very definite step. We strictly reduced it. So how does the left-hand side relate to the right-hand side? It's strictly regulated. So we have indeed derived the inequality for n equals k plus 1 from the assumption, from the assumed inequality for n equals k. And we got the base case at the top of the page. So now you can just declare by induction the thing is true for every n. So that's good. Things you should aim for in when you're writing these out is try and keep the structure of the induction thing clear, base case, make the assumption, declare what you're going to do, summarize what you've done, etc., etc. Think about these things, how you can help yourself find the correct route through. Any questions about that? Is that okay? But the cases where you're dealing with where you're establishing an inequality are harder because it's more hazy about what you should be doing at each stage because there's more freedom. If you just want this to be equal to this thing, that means you're severely restricted with what you can do with each manipulation. So it's easier to find the correct way through. Okay. Any other queries on these ones here? Okay. It is important to get a good feeling for induction. We will see it occur again and again through the course. Okay. Shall we look at some of the ones in chapter 2 then? Yes. I'll be circulating around though in a moment, so we've got individual questions. Okay, so what did we do in the lecture in chapter 2? We just really started it. We looked at the definition of divisibility, and we looked at proofs of the basic properties of divisibility, and then we just quickly discussed the definition of a prime number. We jump to the end of chapter exercises, which are forward on page 22. No, sorry, I jumped the chapter there. Sorry. They're through on page 15. So some of these, the greatest common divisor and Euclidean algorithm we haven't covered yet. But things like question 1, question 4 might be. So question 1 concerns the definition of divisibility. Question 4, again, are induction proofs, but this time it's not an equation, it's not an inequality, it's a divisibility statement that you're being asked to establish by induction. So why don't you have a go at those for a while? I'll circulate around. If you've got individual questions on anything else you've been working on, feel free to ask, and I can give you some. Did you sign the sheet? So if you've got any questions, do ask, and we can do 1 or 2 of these in a moment. Sorry? No, we're skipping over that because they concern stuff we haven't covered yet. Yeah, so I'm just doing. Yeah, we will come back to those. Yeah, yes, it's a little bit all over the shelf.
Jess is coming today.
And after this, I'll be releasing all of the solutions to the Chapter 1 exercises. They'll all be up on Moodle there for you to see. Page 15 for those there. Okay, so let me just skip the little. So you're taking this up. You're taking this up as equal to that. Okay. And then you use these symbols. I think you jumped the gun a bit. I mean, it's good. So remember that when I did that, I put it in a bubble over here because I knew that was what I was trying to. I didn't want to just separate. Yeah. So, well, you know, I mean, this doesn't look a million miles away. This, how would you describe just in general. I mean, again, it isn't. Not down there. And I didn't see it from the further manipulation. Yeah, you want to just get the balance between putting down what you know you're trying to get, but working actually working the right time.
Oh my
Hi there, so the things we're looking at the moment is on page 15. We're looking at some of these questions, the ones with the arrows beside them. There's a question on divisibility there in part 1. And the one parts 4 are more induction proofs. This time about probability statements. Any questions at the moment? Sorry? Okay, great. So we're just having a period where everyone's working away on them, and then I might do more.
In almost all of the cases, this is an odd case where, because of the structure of the kind of makes sense. So that's kind
Oh my god, what a day!
those inequality ones are choice.
Obviously, I don't know what it's about. But I don't know swear.
You wrote maths.
No, you know what it's
I was like, I can't do this.
You're not keeping the thing. You're passing the line. Are not losing, but as long as they're in the right direction.
I'm just like, first time to see you.
Yeah, because it's an influence.
So I would be more like now.
Oh, yeah. So no. Well, no, because if it's a statement like that, it's some claim for every just prove you just offer up one example.
Sometimes
The only thing I'd say I think is to revise the divisibility statement. So this, remember, says A divides equals C. So equals C is the big thing. So you've got the right idea with your numbers, but I think you'd be choosing like A, 10, B, C is like 17.
whatever.
They add together to give you something.
So if you use it before, it means it again.
Oh,
I feel so much about it. It's like,
Not
go to my office.
They are unlimited. So equality even
Can you help me start up?
yeah.
Okay.
Right, to prove it. Yeah. So the first thing is to see what it's saying. It's saying, so it's making a claim about every triple of numbers. It's saying if
They do. It's just that you add them together.
Oh
yeah, that's what it's saying. So it's saying if
Yes, it's family.
so start working with some examples.
Oh yeah, maybe it's good, yeah.
No, because if A is 12 and B is 4 and 3, then 12 divided by 7.
Just be careful, you're quoting the divisibility symbol the wrong way around.
Oh, it's good into it.
When we say x divides y, it's like y is the big part. That can be divided by the x.
Oh, so B and C are the two then.
B and C are, yeah. B plus.
That's so confusing. Who made this?
Well, yeah, but look, but I did, I did do a big warning on the box.
Yeah.
At the start of the chapter.
Yeah.
Yeah, it's unfortunate, but that's, I mean, they didn't, I didn't. That's just the way the notations were.
Why?
Because B can be really big and C can be really small. And then C can be small.
So when I say why, well, tell me that. Give me the example. B and C are 700. This is 4.
No, but that's saying that A just divided to both of them. No, you can have 4, 7, 1. And that would be 4 is divisible by 8.
Yeah, you can think of it divides into. The claim that I made said if A. This statement, like, put a pair of quotes around the whole section. Because we're unsure about whether it's true. It's a claim. The claim says if A divides B equals 3, then A divides B or
It's always that hour.
So, Joseph, tell us about your experiment.
Oh, but neither.
So, explain this.
But it doesn't 4 divided by 7.
True. So this we call a counterexample. It's an example that shows that there is false. Because the claim is making a bold claim about every against. So as long as you find one occasion where it's wrong, then the whole thing falls. Well, yeah. So like if it were in fact true, then you need an algebraic general argument that proves it. But a counterexample is just where the thing is wrong, and you find an example. Here's an example where that proves it's wrong. Just be on the watch for the direction. Correct.
Yeah, I think so. What do you think?
Well, yeah. Yeah, question. Yeah, so, well, you might be moving it or you might be just moving.
Yeah. I just got that crazy expression. First of all, I'm not a number. I'm a human being. That extracts what you said. They're like,
Then, able to buy one of the.
she does that weird song. Do you know about that? What is it? She's like, I don't know.
Yeah, but second, to buy
No,
one
but
as
who
well.
says first one?
Wait,
Wait, so did they call love that?
yeah, we should have another one. She rips off.
First of all,
Did you have to say
I'm a human being.
do you think the same
My
is
favourite
true?
one.
It's that and on the junkie. Oh, yeah. I remember that. Yeah, that's lovely.
Is that this year?
No, I never really told you.
Is that
This is tough because if
Is that
it's true, then
the-
what you gotta do is you gotta
Yeah,
you gotta introduce a general argument.
she got really tall.
big? She's a bit shocking.
So, or you plug into the
I feel
proof
like I've
things,
seen
and then get stuff
the game
because
chat.
they aren't true. You're going to see any So think of situations where you might have a number of people divided into a large number,
50. No,
which is made of flux.
no,
And
not all
it's
over
going to be
100,
false,
sure.
but it isn't true that the A divides B or A divides B. A is 4. So 4 does divide.
You're like, nope, that's Nick, you didn't get to look out.
That would be any example that shows that. So yeah, it's just a few lines. So that thing we call a
It's not the cheap.
it's an example of actually counter.
It's like, not, you do everyone, because she, like, she's just, so she's
Well, this is saying for every it's not 17. It's saying for every n greater than 1, comma, 7.
Just don't answer that question.
Okay then, I've seen some good work as I go around. So we've got a few minutes left. Should we just maybe go through the proof of one of these divisibility statements in question 4? That's just a way to finish off. So we're going to see induction being used again, but in a different way than it was for these summation formulae. So let's choose the first one. The first one, so this is exercise 2.3, question 4, part A. So the claim is for every n bigger than 1, 7 divides 2 to the power of 3n minus 1. Okay, it's an infinite collection of divisibility statements indexed by positive integers, so it's a prime candidate for proof by induction. So you address the base case, which we expect to just be is that true? Does 7 divide 2 to the 3 times 1 minus 1? Yeah. Because that's just 7, isn't it? So yes, base case is true. Quotes, this is something we were considering. Is this true or false? Yeah, it is. 7 clearly divides 7. Everything divides itself. Okay, so we make the assumption. We assume now that 7 divides 2 to the 3k minus 1 for some k larger than 1, bigger than or equal to 1. We're allowed to make that assumption because we already know it's true for k equals 1, so we can assume it's true for something bigger than or equal to 1. Now, the assumption we're making is about divisibility. I think we should unravel that a bit. Right? This question concerns divisibility. We should unravel that statement about divisibility and say what it means exactly. If you look back at the definition of divisibility, x divides y if the second number y can be written as an integer multiple of the first number x.
So this means that 2 to the 3k minus 1 can be written as a multiple of 7. So let's name the associated factor. So we can write 2 to the 3k minus 1 as some multiple of 7. And we've named the other factor as q. So we've kind of fully exposed all parts of the assumption, because we may well need them later on. So now we try and prove the next case. And we prove the statement for n equals k plus 1. Okay, we're going to prove the statement for n equals k plus 1. Here it is down the bottom. 7 divides 2 to the 3 times k plus 1 minus 1. There, it's proved. Okay, yeah, I've just left a big gap. Okay, but what I've done is I've put down my goal. My goal is to prove this. Okay, and the two things we're going to use, just standard algebra about the integers, and we must use the assumptions. Okay. Now, how can we prove this? How can we ever make a claim about divisibility? We can only do it if we've satisfied the definition for divisibility. The definition for divisibility says that 2 to the 3k plus 1 minus 1 is equal to 7 times something. If we can fill this gap with an integer, we can find an integer that goes in there and makes this equation true, then we'll be able to say that 7 divides this. Okay? Because we'll have satisfied the definition of divisibility. Okay? I got 2 minutes to do it. Okay, we need an equation with this power minus 1 equal to 7 times something. So let's start with the power minus 1. We want to get it equal to 7 times something, where the something is an integer. And we want to be able to use our assumption. So any suggestions for how to manipulate this?
Could you split up the powers? That would be like 2 to 3k, and then 2 to the power 3 minus 1, which would equal 2 to the 3k. I don't know actually.
That's good. So you factorized it so that we see 2 to the power 3k, because that's what we see in the assumption. And that's an 8 there. 2 to the 3 is 8. Can we bring in the assumption this way? Be a little bit flexible, a little bit inventive.
Plus the 1 to the other side and then.
Yeah. Just substitute in. So we can move the minus 1 to the other side and substitute in for 2 to the 3k. So we can say 7q plus 1 times 8 minus 1. So what have we got? We've got 7 times 8. 7 times 8 is 56. We've got 56q plus 8 minus 1. So 56q plus 7. So can we fill the gap? Let's instantaneously, because it's 10 to 11. What goes in the gap? Yeah. 8q. Just 8q? Plus 1. Yeah. 8q plus 1. Is 8q plus 1 an integer? Yeah. Q is an integer. So 8 times q plus 1 is certainly an integer. So we have proved divisibility, because our thing is some integer multiple of 7, so we have proved divisibility. So by induction, it's true for all n. Good. So you've got several other, a few other examples to be working on.
I'll click the button on it and I'll release the solutions to the induction questions from the end of chapter 1. So those will all be up there. Keep working away on some more of these, and I'll see you on Monday for lectures in the rest of chapter 2. Okay?